In today's lesson, we are going to look at limits. Now, we've kind of looked at this a little bit in our previous lesson, but now we're actually going to put a term to what we were looking at. So the limit of a sequence is determined by looking where the y values are going. So we want to see where are the y values going, or where are they headed. So if I look at some of the examples from yesterday, we saw this example where our pattern was dividing by 3 every time. So we want to ask the question, where are the y values going? Or in other words, what is the limit of this sequence? And I can look at my fractions to kind of help me figure that out, or continue the pattern to kind of figure that out. So where are they going? Where are they headed? We could say they're headed towards 0. Right? We've talked about this before. They're headed towards 0. If I keep on dividing by 3, I'm going to get a smaller and smaller number, but I'm never going to quite get to 0. So will these y values ever reach the limit? No. I'm never going to reach the limit, but I'm going to get very, very close. Right? If I keep dividing a number by 3 or taking the third of something, I'm never going to quite reach 0. If I look at the next graph, right? So the example from the carbon dating example or scenario. If I keep dividing by half or dividing by 2, or taking half of my amount or half of the previous amount, where am I going to go? Right? Where are the y values going? So if I continue this sequence, 75, we get 37.5. For our next one, we continue to divide by 2. We get 18.75. To divide that by 2, we get 9.375. Divide that by 2, we get 4.6875, and so on. But you can see, even by looking at the graph, where do we keep on going, or where do we head to? Well, we're going to head towards 0. Right? If I keep dividing in half, my number is going to keep getting smaller and smaller, so I'm headed towards 0. Will I ever reach that limit? No. I will never be able to reach 0 if I keep dividing by 2. I will get an extremely small number, but I'll never quite reach 0. The next example, so here I was adding by 6 every time. We saw our linear graph, it was going up by 6. If we were to extend this, where are the y values going? Is there a limit to this sequence? And we talked a bit about this when we referred to our number systems. Right? If this line keeps on going, keeps on extending and extending and extending and going further and further up, is there a limit to this sequence? No. There's no limit, or you could argue that it's approaching 0. Right? So you might think that it's approaching, or the limit is, there's no limit, so you could say that it's approaching or heading towards positive infinity. So there's no real limit, but we're heading towards infinity. So basically there's no limit that we're approaching, because we don't have an actual limit. It just keeps on going forever. And again, if we look at the next example where we were subtracting 15 or decreasing by 15 every time, again, it's the same idea. Where are the y values going? Or in other words, is there a limit, or what is the limit of this sequence? There is no limit. This line will keep on extending down, keep on extending downwards. So there's no limit, and you could say it's headed towards negative infinity in this case. So there's no limit because there is no kind of end point or value that it can't be. It's going to keep on extending to negative infinity. Let's take a look at some new examples. Here we have our table of values and our graph. So let's use our table of values to kind of work through the pattern, or using our graph to help us figure that out. So when we're at 4, we're looking at this value here. It's a little bit more than 3/4 or 0.75. we might say it is 8, or sorry, not 8/10, say it's 4/5. And maybe the next one at 5 is up here. Maybe this is 5/6. Maybe because we're seeing kind of the pattern 1/2 or 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Realistically, it still works out. 4/5 is 0.8. 5/6 is, if I do my math quickly, is 0.83. So it's a little bit higher, and we can see by looking at the two positions that it is a little bit higher, but higher nonetheless. So those could be some possible values for our actual table of values. We can see that from our graph. What is the limit of the y value? Where are the y values going? So if I look at this graph or look at this line, another way we could think of it, of the limit, in terms of where it's going, where is it headed, what value is it approaching, what value is it getting closer and closer to? Well, if we look at these fractions, they're getting closer and closer to a whole. We could predict that the next one is going to be 7/8, then 8/9, 9/10, 10/11, and so on. So where are they going? You could say they're approaching the value of 1. So they're approaching 1. And how do we know? Well, by looking at the graph, you could say the line gets closer and closer to 1. So the line gets closer and closer to 1. You could also argue the fractions get closer and closer to a whole. So different ways you could explain it, but the idea is that you're approaching 1 or getting closer to 1. So essentially the limit for this example here is 1. If I look at the next scenario, so the sequence of numbers goes -5, -10, -5, -10, -5, -10, and so on, and we just repeat that pattern, we want to think, is there a limit to this sequence? And then explain how you know. So depending on your answer, explain. If we were to look at this sequence, is there a single value that it's approaching? Right? It goes -5, -10, -5, -10. So it almost looks something like that. Is there a value that it's approaching? In this case, there is no limit. And the reason that there's no limit, or that the limit does not exist, that might be a better way to explain it or to visualize it. Limit does not exist. And it's because the y values, or these values, do not approach an actual value, or do not approach a single value, or they're not headed anywhere in particular. So y values do not approach a single value. So the y values are not approaching a single value or headed in one direction, right? They're just kind of alternating back and forth between the two. So again, just looking at a little bit at limits in terms of kind of what they mean in terms of looking at a graph or in terms of a number set. In our next example, we're going to look a little bit at a specific type of, or a specific number pattern. So to get us thinking about it, we're going to look at a small activity referring to rabbit population growth. So imagine you're observing a pair of newborn rabbits. After 1 month, they become month-olds. 1 month later, they're adults, and they produce a new pair of newborns. Then those newborns become month-olds, and then the adults reproduce again. So if we want to fill out the following table based on this scenario. Now, it might be a little bit confusing, but we'll work through it. So in month 1, we have a pair of newborns and 1 total pair. The next month, those newborns become month-olds. We still have a single pair. The following month, that month-old pair of rabbits become a pair of adults, and they produce a newborn pair. Next, those newborns become month-olds. Those adults are still adults. So the pairs of newborns there'd be 1 pair of newborns from that adult, and there'd be 3 rabbits in total. Next, we still have the 1 newborn, or 1 pair of adults. This month-old becomes an adult, or a pair of adults, so we have 2. This 1 month-old, or newborns become a month-old, and now these 2 pairs of rabbits makes 2 newborn pairs, so now we're at 5. The next month, these adults are still there, plus the month-olds from before, so now we're at 3. We're at 2 newborn pairs moving into month-olds, and then finally, because of the 3 adults, we have 3 newborn pairs, or 8 rabbits in total. Or 8 pairs of rabbits in total, sorry. Month 7, we still have the 3 adults from before, plus the 2 month-olds. So now we have 5 adult pairs. We have 3 newborn pairs from the previous one. And then finally, because of the 5 adults, or adult pairs, we have 5 newborn pairs. And in total, we have then 13. You could look at it as kind of going in a diagonal in terms of where our rabbits are going. And so on. You could look at it in that sense, where that's kind of where they're moving to. Another way you could think of it is you could look at the columns. You might see a pattern there. Right? 1, 1, 2, 3, 5, 8, 13. If you can imagine the next one, it'd be 21. The next one from that would be 34, 55, and so on. You might see the pattern. The pattern comes from adding the 2 previous values. Right? If we look at it, 1 plus the previous is 1. That's my next one. 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8. 5 and 8 is 13, and so on. So this type of sequence is what we call the Fibonacci sequence. And basically it means, or it's referring to, the next term in the sequence is the sum of the 2 terms before it. So how might you write a mathematical expression to model the growth of this? Right? So kind of how do we come up with a rule that tells us that we have to add up the previous 2 terms? If it helps, we can start off with saying a certain number in the sequence, Fibonacci sequence for the F, just any term or any term in the sequence for n. How would we represent the 2 previous terms? Well, f and then n minus 1, referring to the number before n, and then plus f n minus 2, so the number two positions before. All right, so for example, if I'm looking for position 5, or the term at position 5, this is going to equal the term at position 5 minus 1 plus the term at position 5 minus 2. So this becomes position 4 plus position 3. And if we look back for position 5 here, 5 is equal to position 4 plus position 3. 2 plus 3 is 5. So that does work. So again, this is just kind of more mathematical notation. Don't worry too much, as long as you're understanding that these values are telling us the position or the 2 numbers before. N is any random or any position. Minus 1 refers to the position before that. Minus 2 refers to the 2 positions before that. What happens if you divide a number in the Fibonacci sequence by the one that comes before it? So basically 3 divided by 2, 5 divided by 3, or 5 and 3. So the next one, if we were to go through this, we would have 8 and 5, 13 and 8, We see the first number and the previous one is the second number, so we'd have 21 and 13, and we'd have 34 and 21. So 8 divided by 5, 13 divided by 8, 21 divided by 13, and 34 divided by 21. So what happens when we go through this? 8 divided by 5, we get 1.6. 13 divided by 8, we get 1.625. 21 divided by 13, we get 1.615384. And 34 divided by 21, we get 1.619047. So what do we think, or can we find the limit of this sequence? Right? Maybe if you were to find one more value, what if we did, if we added a 2, so 55 divided by 34, that's the next number, or next sequence. We get 1.6176. So what value do we get closer and closer to? If you look at this, you might find that it's getting closer and closer, or the limit, if you continue this pattern, the limit that it approaches is 1.618. That is the limit that it ends up approaching. So if you continue this sequence and continue this ratio or fraction and find that actual decimal number, you find that it's approaching 1.618. And we'll take a look back at that later. Which Fibonacci numbers are even and which are odd? Is there a pattern? So let's write out these numbers again. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, we'll continue, 89, 144. So this is quite a long sequence of those numbers, which are odd. I'm going to go through and highlight the odd ones. So 1, 1, those are the same ones. So we have those ones are odd, and the even ones are there. So we can kind of see a pattern. There's two odd numbers. Let me actually just fix this so we can see that they're individual. So we have two odd numbers followed by an even. Two odd, one even. Two odd, one even. Two odd, one even. So on. So do you think the 11th Fibonacci number, or the 11th number in this sequence, will be even or odd? And explain your reasoning. Well, if we continue this pattern, we should find that the third number, so if we look at it, the third number, the sixth number, the 9th, and the 12th, those numbers were all even. So if you think about it, or if you see that pattern there, if it's an odd, or sorry, if it's a position that is a multiple of 3, 3, 6, 9, 12, 15, 18, 21, and so on, it would be an even number. Any other position would be odd. So if we go back to the 100th Fibonacci number, so it would be odd because 100 does not evenly divide by 3. So if 100 evenly divided by was evenly divided by 3, it would be an even number based on the pattern that we see here. But because it's not, it would be an odd number. And if you were to continue this pattern, you would find that the 100th Fibonacci number would in fact be odd. The last activity, what we want to do is just kind of draw our own golden spiral. The idea behind this Fibonacci number, this ratio, if you Google 1.6618, you'll find that this number or this spiral occurs in many different things, in art, in nature, in architecture. And it's considered the golden ratio. So it's kind of what they used, or they've recognized this ratio in the past, and they just consider it to be a very special or a very important ratio in terms of how things appear. And again, you can Google golden ratio or the golden spiral or Fibonacci sequence, and you'll find all examples in nature and art and things like that of where we can actually see these this ratio actually play out. So let's draw one of our golden spirals. So what we're going to do, every time we see a value, we're going to draw a square in those dimensions. So we have a 1 by 1 square for a first one. Use a second color, and we have another 1 by 1 square. Next we have a 2 by 2. So I'm going to draw a 2 by 2 square that connects it. Next we have a 3 by 3 square. So we can kind of see a 3 by 3 square that fits there. Next we have a 5 by 5. And we can see that it nicely lines up with our actual shape. After that, we have an 8 by 8, which again lines up with this entire side. 6, I think that's 8 there. After this, we'd have a 13 by 13 square. Not too sure if I can fit it on here. See, 1, 2, 3, 4, 5, 6, 7, 8. No, unfortunately I cannot. Maybe if I was to rotate this a different way or move this up, I might be able to fit in the next one. But this is kind of the rough example of our golden spiral. And we can see that if we kind of start out in the one corner, we kind of see that kind of golden ratio kind of start there and form. Obviously, it can be drawn a little bit better than I have there. So what are the squares growing by? Or what is the factor that they're growing by? And the factor that they're growing by is that number that we found, that 1.618. Right? And the reason that we know this is that we found the ratio by dividing. Right? 1 by 1 divided, and so on. Because we did that in the last table. So we've connected the squares, we've kind of drawn a rough spiral. You could color those images in or those squares in if you wanted to get kind of an art piece. And now try to look or Google examples of where this spiral can be found in art, nature, architecture, etc. Again, if you Google Fibonacci numbers or the golden ratio, you'll find many different examples. But take a look and please try to go through and Google just to see kind of where this sequence of numbers does appear in nature. And it's kind of unique and interesting because there is this number set, this pattern that you can come up with where you're just adding the two previous numbers. And when you kind of explore it a little bit, map it out, you'll find that this number also occurs in nature where it doesn't really, where you might not expect it to. You might not expect things in nature to kind of follow this mathematical pattern, especially in the examples that you see. So it is quite interesting, so I do recommend you taking a look. But again, the main thing from this lesson is, again, looking at limits, seeing what numbers approach to, and then again, just looking at a different number set and looking at patterns.